How are you all doing today? Good.
Pretty fine.
All right. Howdy. So today we are going to be talking about inductance, and then we will be looking at some circuits that contain both inductors and capacitors in them as a precursor to our series on transient analysis of RL and RC circuits, which is our next big topic that will start tomorrow. And that lecture will be spread over 3 days, and that'll be the last topic on our exam. So, orient my computer correctly. So today, as I said, we are going to talk about inductors and inductance. So, what an inductor is really just a coil of wire. So let's say that we have a cylindrical core, something like this, and we wrap a wire around it. This is the basic shape of an inductor. We might pass some current, I of t, into one portion of the wire, and that would obviously then return down here like so. So what an inductor is it's another energy storage device, very similar to a capacitor. But in a capacitor, we saw that the energy storage occurred due to the presence of an electric field caused by the separation of charges. In an inductor, we're going to see energy storage that is caused by what's called magnetic flux being concentrated inside the coil. So if any of you guys have had physics 202 by this point, you may be aware that if we have a wire or a section of a wire carrying a steady current I, then there will be generated magnetic field due to this movement of charge carriers. And that magnetic field winds up forming little loops around the wire where the direction of the field is dependent on the direction of the current, like so. So it's just forming concentric loops all along the wire. Well, in a solenoidal coil, which is what I have drawn on the left, and which is how most inductors are constructed, what winds up happening is that the magnetic field gets concentrated inside that coil. And that magnetic field or magnetic flux is what is the energy storage. As soon as we change the amount of the current, then like say if we reduce the current, then that means that we are releasing some energy into the system. If we push more current through the coil, that means that we're trying to absorb more energy from the system. So inductance, L, may be considered as a constant of proportionality between phi b, which is magnetic flux, and I, which is simply the current that causes the magnetic flux to occur. Now, from Faraday's law of induction, the voltage drop across such a inductor coil is simply negative the derivative of the magnetic flux as a function of time, which using our other relationship here is going to give us L times the derivative of the current with respect to time. So this is one of those fundamental equations like we had the other day. So I'm going to put a red box around it. In our inductor, let me draw a picture of the schematic diagram symbol like so. It looks like a coil of wire having some value L. The voltage drop over the inductor will be here, V of t, or we might call it VL of t, and the current I of t flows like so that we obey the passive sign convention. The units of inductance are the Henry. So a Henry, 1 Henry, is defined as 1 volt second per amp, which is the exact same thing as 1 ohm second. We got our units and all that kind of good stuff. So if we look at this first equation that we've developed here, we can actually come up with two very important properties about inductors, okay? And they are both related to the rate of change of the current. So our first property will deal with DC circuits, which means that the current is not changing at all. So if we have a constant current, then it stands to reason that our derivative relationship here is 0, which means that for any DC circuit, an inductor may be treated like a short circuit. Okay, so this is exactly opposite what we observed in a capacitor. In a capacitor for DC circuits, we treated them as open circuits. For inductors in DC circuits, we treat them as short circuits. This equation that we have developed here that I've labeled as 1, put in a red box, should look vaguely familiar as well. It is the exact same equation that we had for capacitors, except that everywhere we had voltage, we replace it with current. Everywhere we had current, we replace it with voltage, and we replace all our C's with L's. Capacitors and inductors are what are called electrical duals. So they're going to have the exact same relationships between them, except that the current and voltage relationships are going to be swapped. All right. So if we take equation 1, oh, sorry, we have a second thing to look at here. My apologies. Another thing that we can observe is that the current flowing through the inductor cannot change abruptly, right? Effectively, that di by dt term cannot approach infinity because that will give us an infinitely large voltage, which infers that we are having an infinitely large transfer of energy in an infinitely small amount of time, which obviously cannot occur. So statement number 2, the current through an inductor cannot change abruptly. Again, this is exactly opposite what we observed in capacitors last Thursday. In a capacitor, it's the voltage drop that it cannot change abruptly. All right, so if we take equation 1 and we rearrange it slightly and integrate, we can develop a different relationship. So we would have I of t is equal to 1 over L times the integral from negative infinity to t of v of t prime dt prime, which we can rewrite as 1 over L times the integral from t naught to t dt prime dt plus I of t naught, where I of t naught represents the initial condition where we know what the current flowing through the inductor is at some past point in time. So just like capacitors, inductors also have memory in as much as the current flowing through an inductor depends on past values of that same current. So I want to work a quick example problem here. Let's say that we have the following inductor having a value of 5 henries. We are trying to determine the current flowing through it, and we're going to be given a voltage waveform across it. So this is going to be V of t measured in volts on this axis, and this is going to be time on this axis. So let's say that our voltage looks something like this. It is 0 until it shifts abruptly up to 20 volts. It's going to stay 20 volts, and then it's going to shift abruptly back down 0 volts like so. And let's say that this shift up occurs at 1 second. Here's 2, comes down at 3, and then we have 4, 5, 6, etc. What we want to do is figure out how the current is going to behave under the assumption that I of 0 is equal to 0 amps. Here will be I of t measured in amps, and here's time measured in seconds. Okay. So since we know the voltage, we're going to use the second equation, which I'll go ahead and put a box around because it's another very important equation. Like so. We could write our voltage as a piecewise function. So we could say that V of t is 0 volts for t less than 1 second. It's also 0 volts for t greater than 3 seconds. And it's 20 volts when 1 second is less than t is less than 3 seconds. Does that piecewise definition for our voltage seem reasonable to you all?
Yes, sir.
Yes.
All right. So if we use our integral-based relationship, we could say, let's see, so for t less than 1 second, we would have I of t is equal to 1 over 5 henries times the integral from 0 to t of 0 volts dt prime plus I at 0. What would the result of this integration be?
It'd just be whatever the current is at 0.
Right, which is listed right here as 0 amps. So over this particular time interval from 0 to 1, our current is exactly 0 amps. Let's look at what happens for t less than, or excuse me, when t is between 1 and 3 seconds. So let's see, 1 second less than t less than 3 seconds. All right. So we're going to have I of t now is the integral, 1 over 5 henries times the integral from 1 second to t of our voltage over this range was 20 volts dt at 1 second. So this is going to look like, let's see, 1 over 5 henries times 20 volts times time evaluated at time t and time, excuse me, that should be 0, that should be 1 second. Plus I at 1 second. So I want to be clear here. This I at 1 second part is this answer right here. We know that over the time interval from 0 seconds to 1 second, our current has a constant value of 0 amps. So this guy right here is 0 amps. So what we have left here, 20 volts over 5 henries is going to look like 4 amps per second.
Why are you going from 1 second to time t instead of 3 seconds up there?
Fantastic question. So the reason why I'm doing it from 1 second to time t is because I want to know how this guy behaves over that interval. If I had a definite integral on both sides, I would get a numerical answer which would only be valid at exactly t is equal to 3 seconds. So if I want to know how this guy behaves as a function of time, then I need to leave time in my integral. Does that make sense?
Yeah, I got it.
Okay. So we'll have 4 amps per second, which is the result of dividing volts by henries. And then here, we're going to have t minus 1, where our units here are, or I guess I should just put it explicitly as t minus 1 second. So what this is going to look like graphically, if we come back up here to our graph, I'm going to put 8 amps right here, is that in 2 seconds, our current is going to increase until it takes a value of 8 amps. So it is increasing at a rate of 4 amps per second, which is exactly the slope that we found from our integration. And it looks like it's just time shifted to the right by 1 second, which is what that t minus 1 second does. All right, so everything seems hunky-dory there. Now we go for the interval t is greater than 3 seconds. I of t will look like 1 over 5 henries times the integral from 3 seconds to t of 0 volts dt prime plus I at 3 seconds, where the I at 3 seconds comes from this bit right here. So the integral part of it is obviously going to be 0 amps. When we evaluate our previous expression at exactly 3 seconds, we have 4 amps per second times 3 seconds minus 1 second gives us 8 amps. So we would observe that our inductor would carry a current of exactly 8 amps in perpetuity. Okay, this is not technically true. All right, so in theory, because we are dealing with an ideal inductor, it can store its current forever. But inductors are made of wire, and wires have a finite amount of resistance. So really, eventually, we would see that this current would decay to 0 as the resistance of the wire converted that stored energy into heat. That is exactly all that the transient analysis that we are going to start doing on Tuesday or tomorrow is about, is mathematically describing how that inductor converts energy into heat through a resistance, okay? But we can see here that since our inductor, our ideal inductor, stores 8 amps of current internally or forces 8 amps of current to flow, that's why it's behaving as if it's a temporary energy storage element, right? We applied a voltage of 20 volts for a period of 2 seconds, causing a current of 8 amps to flow through the inductor, and that current of 8 amps will flow as long as we don't introduce anything into the system that will convert its stored energy into heat. So with that being said, we can now develop relationships for power and energy for an inductor. So power will always be the product of the voltage and the current. So in this case, that's going to look like L times I times the derivative of I, which is, again, extraordinarily similar to what we observed with capacitors. And our energy relationship, which I'm going to skip the derivation because it is absolutely identical to what we did with capacitors, winds up becoming 1/2 L I squared. So we have 4 relationships for inductors, just like we had 4 relationships for capacitors, and they are all extraordinarily similarly derived, right? So as a brief recap here, capacitor C who is obeying sorry, I'm going to need to save this and exit real quick because I'm going to keep getting that silly error. So we have a capacitor obeying the passive sign convention, V of t like so. And on this side, I'm going to draw an inductor having a value of L, also obeying the passive sign convention. For our capacitors, we had the relationship that I was C dV by dt. For inductors, we observed that V was L di by dt. Exact same equation. We're just replacing I with V, V with I, and L with C, and vice versa. We also got the equation V of t was equal to 1 over C integral from t naught to t of I of t prime dt prime plus V at t naught. So for our inductor, we will have I of t is equal to 1 over L integral from t naught to t of V t prime dt prime plus V of t naught. Our power relationship was C V dV by dt. For capacitors and for inductors, it was L I di by dt. And finally, we have our energy relationships. W is equal to 1/2 C V squared for capacitors, and W is equal to 1/2 L I squared for inductors. So just writing all this down to show you there's really only one set of equations that you need to know because the capacitor and inductor relationships are identical. They're just replacing current with voltage. All right, so those are all of our relationships. Now let's talk about how we can combine inductors. So if we have a network containing multiple inductors in series, like so, this guy VL1, this guy VL2, and this guy VLN, just based on the relationship between inductors and capacitors, how do you think this is going to turn out? Anybody have any clue? Any thoughts at all?
in series, you do their reciprocal, and then in parallel, you add them up.
So in series, adding the reciprocals, that was how a capacitor behaved, right? But the capacitor is the opposite of the inductor. So for those of you who didn't attend class on Thursday, we found out that capacitors in series combine like resistors in parallel. And so I would argue that since we have the exact same relationship, except that current and voltage is switched, we should expect to see that inductors in series combine in the opposite way that capacitors do, which means inductors in series should add like resistors in series. And we can prove that rather easily, right? So I could say that V of t is equal to VL1 plus VL2 plus VLN, where I can express all of these voltages. So that VL1 would be L1 di by dt, VL2 would be L2 di by dt, and VLN would be Ln di by dt. And then I can group all of my like terms together. So everything has a common factor of the derivative of the current. So that's going to look like L1 plus L2 plus Ln di by dt, which we could say is Leq di by dt, where Leq, our equivalent inductance, is L1 plus L2 plus Ln, or simply the sum from I is equal to 1 to n of Li. So inductors in series add like resistors in series. If we had some number of inductors connected in parallel, so we have a network over which there is some voltage V of t, call this guy L1, 2, I'm going to call this current IL1, IL2, and ILN. We could observe using Kirchhoff's current law, let me express this as the current I of t entering, that we would have I of t is equal to IL1 plus IL2 plus ILN, which is the same as 1 over L1 times the integral from negative infinity to t of V of t dt plus 1 over L2 times the integral from negative infinity to t of V of t prime dt prime all the way out to 1 over L sub n integral negative infinity to t V of t prime dt prime. And so all of those integral terms are exactly identical. So we could have 1 over L1 plus 1 over L2 plus 1 over L sub n, all multiplied by our integral. Which is going to look like 1 over LEQ times the integral. Where, in this case, our equivalent inductance of all of our inductors connected in parallel looks like 1 over L1 plus 1 over L2 plus 1 over L sub n to the negative 1, or the sum from I is equal to 1 to n of 1 over L sub I, this whole thing. Or an easier way, inductors in parallel add like resistors in parallel. All right, so that's what I have prepared specifically regarding inductors. So before we move on to circuits that contain both inductors and capacitors, are there any questions? Is there anything anybody would like me to re-go over? Anything you want to ask me about?
So for inductors in parallel, they have the same current through each of the inductors?
No, by definition, inductors in parallel have the same voltage across all of them. Because that's how, so that inductors still have to obey Kirchhoff's current law and Kirchhoff's voltage law. So inductors in parallel have to have the exact same voltage drop across them. And the current through the inductor is related to both the voltage across the inductor and the inductor value itself. But it's not a simple relationship like we saw with resistors. There's an integral involved. Can I scroll up to the inductors in series? Absolutely. So I want to be clear here. I do not expect you guys to ever have to derive this junk that I derive. Knowing the last bit there, that inductors in series add like resistors in series, is absolutely enough to solve anything that I'm going to throw at you. Similarly, inductors in parallel combining like resistors in parallel is also going to be good enough. The derivation is there for other math dorks like me to see, but it isn't necessary for the overwhelming majority of you. Any other questions over what we've covered thus far? All right, so what I would like to do next is we're going to work 2 homework problems from homework set number 12, which are, in my opinion, the 2 most difficult homework problems that were assigned to you this entire quarter. All right, and we're going to use our inductor and capacitor relationships to figure out exactly what the heck is going on here. So these are wonderful practice for understanding these inductor and capacitor relationships. So for our first problem, which happens to be homework 12 number 3, our circuit of interest is a voltage source connected to an inductor connected to a capacitor where everything is in series. Our inductor has a value of 2 millihenries. Our capacitor has a value of 80 nanofarads. And we are told that the capacitor voltage Vc of t has a value of 4 cosine 10 to the 5 t volts. And we want to figure out what Vs of t is, okay? So this circuit only has 3 elements in it, and it legitimately might be the hardest problem that you guys have ever seen until we work the next problem that we're going to work. Do any of you have any thoughts about what our approach could be? Or have any idea whatsoever how we might, like, not the specifics, but just a general idea of how we might solve for Vs of t?
Apply KVL.
Kirchhoff's voltage law, absolutely right, okay? Our simple relationships, KCL, KVL, not Ohm's law because we don't have resistors technically, but KCL and KVL are absolutely the right way to approach this guy, okay? So I'm going to write this in blue. I'm going to arbitrarily say that this is the polarity of my inductor voltage, VL of t, and this is my common current, I of t, okay? So I know that Vs of t will be equal to VL of t plus Vc of t. Does anybody have any problems with that? I have applied Kirchhoff's voltage law exactly as the gentleman who spoke suggested.
Good so far.
All right, everything looking good so far. So what I am going to do now is for me to figure out what that voltage VL of t is. Does anybody have any thoughts about that, right? We know what this guy is. We don't know what this guy is. And we don't know what this guy is. So we're in a little bit of a pickle. Any thoughts on figuring out VL of t?
We find the currents going through VC based on the VC formula that we have, and then we say it's the same current going through VL, and then put that into the equation for VL to find.
Absolutely correct. So we know that VL is L di by dt. And we also know that since both elements have the same current flowing through them, I of t is both the current flowing through the inductor and the current flowing through the capacitor. So this is going to, so let's see, we're going to have L times the derivative with respect to time of, let's see, how do we find the current flowing through the capacitor is going to be C times the derivative of VC with respect to time. plus VC of t, right? So I've used both of those derivative-based relationships that we've learned, and I can now combine things here. So I can just say that this is LC times the second derivative of my given capacitor voltage plus my capacitor voltage, which mathematically that's more succinct, but doing it in practice actually might be more difficult. So I'm just going to move this over here. All right, so how are we going to do this math? Anybody have any ideas?
I have a question.
Sure.
In the previous step, L d over dt times C, is that dVc of t over dt or dVl of t over dt?
I'm sorry, that is the DVC. So let me try to have better handwriting there.
And how did you get it to be the second derivative of the Vc?
Well, because I'm taking the derivative of the derivative with respect to time.
Okay, so you have the C taken out. Okay, thank you.
So we have an L of 2 millihenries. So let's look at this thing here. So 2 millihenries, so that's going to be 2 times 10 to the minus 3 volt second per amp times 80 nanofarads, 80 times 10 to the minus 9 amp second per volt. So my volts cancel each other, my amps cancel each other, so I'm going to have something seconds squared there. Let's see, 4 cosine 10 to the 5 t volts, close that bracket, plus 4 cosine 10 to the 5 t volts. All right, so let's do this multiplication part here to make things a little less awkward. So 2 times 80 is going to be 160. Then we have 10 to the minus 3 and 10 to the minus 9, so that is going to be 160 times 10 to the minus 12 seconds squared. How do we take the derivative of this cosine guy right here? Let's worry about the first derivative for now.
Negative 4 times 10 to the 5 sine 10 to the 5 TV.
So negative 4 times 10 to the 5.
Sine.
Well, so let's look at the units here real quick. So the 4 gives us a unit of volts, and the 10 to the 5 is going to give us units of per second. So I'm saying that because 10 to the 5 is an angular frequency, meaning that it has a units of radians per second, where radians is a dimensionless quantity. So this is going to be volts per second. Then we have sine 10 to the 5 t, like so, okay. Plus our 4 cosine 10 to the 5 t volts out here. All right. So what happens when we take the derivative again?
Yeah, not just be -4 times 10 to the 10th volt per second squared.
All right, so we're gonna have another, yeah, so we're gonna have another 10 to the 5 come out, having a units of per second. So that would give us -4 times 10 to the 10 volts per second squared, which is exactly what you just said. So you're perfectly correct. So what happens when we take the derivative of sine?
Should just be cosine.
Cosine. Close this guy right here. Plus 4 cosine 10 to the 5t volts. All right, so now we got a little bit of math to do. So we have 160 times -4. That's -640 times 10 to the -12 times 10 to the +10. Looks like -6.4. So -6.4 cosine 10 to the 5t plus 4 cosine 10 to the 5t. Both of these have units of volts. Is just going to look like -2.4 cosine 10 to the 5t volts. So for this particular problem, what do you guys feel was the hardest part of this problem? What I think doesn't matter.
Algebra.
Algebra, okay. Yeah, I would argue that paying attention to the units and all of that kind of stuff, probably pretty difficult / quite important, because it could be easy to get the bit where we did the second derivative, the units being off on that would obviously mess everything up. So paying attention to that kind of stuff is a big deal. The circuit analysis, though, in my opinion, just applying KVL seems pretty straightforward, because this is a single loop circuit where all of the elements were connected in series. Whenever we had a single loop circuit, when we had just a DC circuit, that was usually our go-to move, and it's exactly the same thing here, right? So from a circuit analysis perspective, it's fairly straightforward. It's just the math that gets nasty. I feel like the setup of the equation is my downfall. That's fair. I hope that this step was fairly straightforward, because that's just simple KVL. This step, I hope, was also fairly straightforward. That's just trying to put things in terms of what we know and what's common to our system. And then this step is just taking that previous step one step further. Okay, so I definitely believe that this is legitimately the hardest problem that you guys have seen in this class to this point. Let's go one step harder, I think, and then we'll be done for the day. And I want you guys, particularly the three of you who said you have trouble setting up equations, to be the ones that try to help me out as much as possible here. So in this particular circuit, we have some voltage source Vs of t. Then we have an 8 millifarad capacitor in series with a 24 millifarad capacitor. And these guys are in parallel with a 20 millihenry inductor. We are told that there is some current Is of t leaving, sorry, our voltage source, which I don't know why I put an arrow there. Should be a plus and a minus sign. So let's see, we are told that Vs of t is 75 e to the minus 100t millivolts. We are told that Is at 0 minus is negative 50 milliamps. And we are asked to solve for Is of t for t greater than 0. So, Sarah, what do you think our first step should be in this particular problem?
It's either KVL or KCL, but I think it would be KVL because we have a volt source.
Okay, so before we even get to that point, though, there's a simplification that we can make.
I can only assume it goes with the capacitors being, if you add them whenever they're, damn it. You do the thing with the capacitors.
Okay, so we're going to combine the capacitors. So you seem a little bit frustrated right now, which is perfectly okay. So I'm going to call on somebody else. Kennedy, how do you combine the? Well, actually, you were not here on last Thursday. We talked about it briefly, but somebody else, anybody, tell me how to combine those two capacitors in series.
Combine them like you would in parallel, like you would resistors in parallel.
All right, so that would be 8 times 24 over 8 plus 24. So somebody tell me what that's going to be.
6 microfarad.
6 milli. My handwriting might be terrible
Yeah.
there. That should be lowercase m, which is milli. 6 millifarad. All right. So now let's get back to what Sarah said just a moment ago. It's going to be either KCL or KVL, which is absolutely correct. This is a single node pair circuit where everything is connected in parallel. So I would argue that we should be doing KCL, Kirchhoff's current law, since that is how we handled all of our single node pair circuits back when we were dealing with those on like the 3rd day of class, right? KVL would be less appropriate because since everything is in parallel, all we're going to find is that the voltage drop over everything is the voltage drop that we're given, which doesn't really provide us with any new information. So applying KCL, I'm going to specify that this will be my capacitor current, IC of t, and this guy right here will be my inductor current, IL of t. And I can say then that IS of t, which we don't know, is equal to IC of t, which we don't know, plus IL of t. which we also don't know. So it might look right now that writing this equation didn't really get us anywhere, but we can write IC of t in terms of our voltage. And we can also write IL of t in terms of our voltage, okay? So the capacitor current, IC of t, is going to be C times the derivative of the voltage across our capacitor, which is Vs of t, with respect to time. So we're getting somewhere. So I'm going to put a check question mark here because we don't know it, but we know how to do it, I think. And then over here for my inductor current, I'm going to have 1 over L times the integral from, I'm going to say 0 because we're given a current at time 0. So that seems like it's going to be the time that we're where we know stuff at. IL of t, Vs of t prime, dt prime plus IL at 0. So this is another thing that we don't know, but I feel like we can figure out how to do it because it's just integrating something we're given. And this guy over here, this initial condition, is probably something that we just don't know right now. So which part do you guys want to do first? The derivative portion or the integral portion?
Start with the derivative.
The derivative, okay? So C, let's breaking this guy into easily digestible chunks. So our capacitor current is C times the derivative of our source voltage with respect to time. So that's going to be 6 millifarads. So that's 6 times 10 to the minus 3 amp seconds per volt times the derivative of 75 times 10 to the minus 3 e to the minus 100 t volts. So what's 6 times 75? So that is 450. Does that sound right? Amp seconds. So that's just me multiplying the 450 times 10 to the minus 6. That's me multiplying 6 times 10 to the minus 3 times 75 times 10 to the minus 3. I think I did my mental math correctly. Yeah. So how am I going to take that derivative of e to the minus 100t?
It's gonna be minus 100 times 75 times 10 to the negative 3 times e to the negative 100t.
All right, so negative 100. So this is going to have units of per second. We talked about why in our last class, I believe, with one of the example problems that I worked, but essentially we want the argument of the exponent to be unitless. So if time is measured in seconds, then that 100 has to have units of per second. All right, so then we're going to have e to the minus 100t. We've taken care of our volts. All right, so 450 times 10 to the minus 6 times negative 100 looks like 4.5 times 10 to the minus 2. Amps. Or a smarter way to do this might be just calling it negative 45 milliamps at this point. Right, because my second and my per seconds cancel each other. E to the minus 100t. All right, so we got this guy taken care of. I guess now we will suffer through the derivative portion. All right, or excuse me, the integral portion. So 1 over, let's see, L was 20 millihenries. 10 to the minus 3 volts second per amp. So that's 1 over L. We're going to integrate from 0 seconds to t. And we are integrating 75 times 10 to the minus 3 volts, e to the minus 100 t prime dt prime. So that's going to be 75 times 10 to the minus 3 over 20 times 10 to the minus 3. So that just looks like 3.75. And then we have amps per volt second being multiplied by volts. So that just looks like amps per second. Integral from 0 to t of e to the minus 100 t prime dt. So how do I do that integral?
That would be negative 1 over 100 e to negative 100 t.
Negative 1 over 100 per second. All right. So the seconds and the per seconds are going to cancel each other out. And then I'll have e to the negative 100 t prime evaluated at t and 0. Right. So that's going to be negative 37.5 e to the minus 100t minus 1, right? We can't forget that there's going to be an e to the 0 that we have to take care of there as well. If we forget that, we are going to have some issues. Sorry, and this should be negative 37.5 milliamps. All right. So to be clear here, we now know this part. And we also know this part. Any thoughts on how we're going to get this guy right here?
Is it the current source with the 0 negative term?
So that is our source current at t is equal to 0. I guess it doesn't necessarily have to have the 0 minus thing right here. I'm just used to writing things that way. So that is our source current at exactly t is equal to 0. So let me ask you guys a question here. Kirchhoff's current law, which is the law of conservation of charge, has to be valid in all of our circuits. It has to be valid in all of our circuits at all points in time. So I would argue that IS at 0 will be equal to IC at 0 plus IL at 0. Does that make sense? So effectively what I am saying is at the exact instant in time where t is equal to 0, Kirchhoff's current law must still be valid. Can anybody think of a reason why this isn't true? All right, nobody's saying much of anything. So, which of these terms do we know?
IS at 0.
All right, IS of 0. Okay, so we don't know that one. We're obviously trying to find this one. Any thoughts on how we might find IC at 0?
Would you just plug in 0?
Yeah, we literally just plug in 0 into the equation that we derived for IC. So, was that Dylan speaking? Austin, okay, my apologies. Austin, based on what our equation is, what is IC at 0?
Wouldn't it just be negative 45 milliamps?
That's exactly correct. So this guy is negative 45 milliamps. This guy was negative 50 milliamps. So what does it have to be in order to satisfy Kirchhoff's current law?
Should just be -5.
Yeah. Negative 5 milliamps. So we would put that in. We now know this guy. So our last step is to just put all this junk together, right? So IS of t is going to be IC of t, which was negative 45 e to the minus 100 t milliamps, plus IL of t, which we found to be negative 37.5 milliamps times e to the minus 100t minus 1 plus IL at t is equal to 0, which was negative 5 milliamps. And so I'm going to kind of group some things together here, right? So obviously I have negative 45 milliamps minus 37.5 milliamps, and both of those are multiplied by a factor of e to the 100t, right? So I'm saying negative 45 milliamps minus 37.5 milliamps times e to the minus 100t. And then I have plus negative 37.5 milliamps minus 5 milliamps. These are my constant terms, right? Actually, I have negative and negative, so this guy should be positive, right? This negative sign multiplied by this negative sign gives me positive. So negative 45 minus 37.5, negative 82.5 e to the minus 100t plus 32.5 milliamps. This is, without a doubt, the hardest homework problem that you guys will be given in this class, including everything that we have yet to cover. Okay. Thoughts?
How did you get IC at 0 seconds again? The negative
Okay.
40.
So we literally just plug in t is equal to 0 here, which means we're going to have negative 45 milliamps times e to the 0, which is just 1. So we have negative 45 milliamps times 1 is negative 45 milliamps. Any other questions or anything?
Can you scroll down?
All right, I would like to work one more example problem that in my opinion will be much, much easier. We'll consider it kind of a palate cleanser, if you will, for this material. This would be much more in line with one of the questions I may ask on your upcoming exam, which I believe is supposed to be happening the Thursday of next week. So let's say that I have the following circuit. Sorry, that shouldn't be 8 volts, it should be 8 ohms. In this circuit, I want to know the energy stored in the capacitor and the energy stored in the inductor. All right, so let me ask what I hope to be a simple question first. If I want to know the energy stored in the capacitor, do I need to know the capacitor voltage or the capacitor current?
Voltage?
Okay, the capacitor voltage. Does it matter what polarity I assign to the capacitor voltage?
No.
No, because the energy is dependent on the voltage squared. So I'm going to call this guy right here VC. For my inductor energy, do I need to know the voltage drop across the inductor or the current flowing through the inductor to determine its energy?
The current flowing through it.
Current flowing through it, okay. So I'm going to call this current IL. Also, the direction of this particular current does not matter since the energy stored is dependent on the current squared. So, another question, I hope easy. Is this a DC circuit or a non-DC circuit?
DC.
All right, it is a DC circuit because our only source in the system is a DC source. So if our excitation is a DC signal, then we have a DC circuit. So to a DC circuit, what does our capacitor look like?
Wouldn't that be an open circuit?
An open circuit, okay? And to a DC circuit, what does our inductor look like?
Short.
Short circuit, okay. So I'm going to redraw this guy. Does anybody see any problems in the way that I've redrawn this guy? Are these two circuits equivalent if we are treating our capacitor as an open circuit and our inductor as a short circuit?
Looks good to me.
All right. So how would I solve for the quantity VC?
Voltage division.
All right. So VC would be equal to what then, using voltage division?
12 volts.
My equation looks like 12 volts.
8 divided by 18.
All right. So that's the resistor we're interested in, which is the 8 ohm resistor divided by the total series resistance seen by the known voltage. So let's see, that's going to be 8 times 2/3, which of course isn't something pretty. Let's say 16 thirds of a volt. So our energy stored then will be 1/2 times half of a farad times 16 thirds of a volt squared. So let's see, 16 times 16 is 196. 2 times 2 is 4 times 9, 196 over 36. And obviously that can be simplified, but I'm being lazy. Somebody else, tell me how I get my inductor current.
You know the voltage VC, and you know that 8 ohm resistor, so you just find the current flowing through that. Since everything's in series, it should be the same.
Okay, I would be slightly lazier than that personally. I would call it 12 volts over 18 ohms looks like 2/3 of an amp, right? Your way, using the voltage drop over the capacitor and the capacitor, the voltage drop over the capacitor and the resistance of the resistor in parallel with the capacitor, absolutely correct. But I guess I'm just being contrary today for whatever reason. Our inductor energy then is going to be 1/2 times, let's see, 2 henries times 2/3 of an amp squared. So that should be 4/9 of a joule. All right. So that question is literally one I've asked on an old test, just different numbers because I made them up. Okay, so we're getting out roughly 20 minutes early, which is okay by me. Do you guys have any other questions regarding capacitors and inductors before we get into transient analysis tomorrow? Our transient analysis is going to be largely dependent on really kind of just remembering the rules for capacitors and inductors. Specifically, the current through an inductor cannot change abruptly, and the voltage drop over a capacitor cannot change abruptly. Everything else is going to be fairly straightforward. So, any questions? Alrighty, well, I will see you guys tomorrow morning at 10 a.m. I hope to have both the capacitor lecture and this inductor lecture up on YouTube and Moodle this evening. So I'll see you guys tomorrow.